Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This is episode 21 where I want to talk about the 4K demo that we just put out called Makeshift. Now this is actually something I was pretty excited about. I started working on this, different parts of it at different sort of stages. Some of the oldest code is actually from when I was about 17, maybe 18. And the newest code, of course, is less than a week old right now. So yeah, it's been pretty cool, and I was really happy to do it. Always wanted to do a C64 demo. Finally did one. Yeah, generally, I'm pretty happy about it. This, by the way, is a C64. This is the old style. I can show you what these look like. This one's that one's really dusty. Hold on. Grab the other one. This is what it looks like. The Commodore 64. This is a beautiful, beautiful key cover. Pleather. And here is the old bread bin. They call it a bread bin because it's kind of shaped like a bread bin. Kind of a goofy looking thing. Love to show off the mechanical shift lock. Awesome. So there's the old style. We've also got the new style. Hold on. Which looks something like this. Sort of looks like an Amiga, but a lot smaller. And yeah. For those of you guys that are unfamiliar with this system, let me pull up some specs. I'm actually making sort of some presentation slides for this. I didn't really have enough time to make that many of them for this, but I'll be giving a small presentation about this at work tomorrow as well. So I thought I would just dig into this a little bit. Anyway, a little bit of specs on the C64. The CPU is a MOS 6510. This is basically a 6502 if you guys are familiar with that, and you should be if you're not. It runs at a little under 1 megahertz in PAL regions. It runs a little bit over that in NTSC regions. But of course, that doesn't turn out to be an advantage because really what matters when you're doing a demo is how many cycles do you have per frame, and you end up having way more in the PAL region, even though the speed is slower. For memory, we've got 64 kilobytes. Most of that is shared, so the whole 64K of memory is shared between the CPU and the video chip. There's actually a little bit more memory than that. First of all, two of the addresses are actually kind of hard to get at because they're beneath some IO mapped ports within the processor. So to actually read and write those is possible, but very difficult. And then you actually have a little bit more memory than that, but it's 4-bit memory and it's used for colors. Anyway, it's pretty cool. But yeah, you can actually directly access that. And in this demo, we don't do that very often because it was one of the ways that I was able to save space. In terms of the graphics resolution, normally it runs at 320 by 200 pixels. That's, the sort of main screen area. I think in the next slide here, one of these slides, here we go. I actually have a C64 here, and you can see this is sort of what the screen looks like when it's going. So you have this sort of border area and this character area. This character area, this is the thing that's 320 by 200 pixels. In high res. There's also a multicolor mode where it's actually half the horizontal resolution in order to get twice the bit depth per pixel. So that's what that looks like. It is actually possible. It wasn't never intended for this to be possible, but it is totally possible to draw stuff in the borders. However, it's very limited, and in this demo, I chose not to do a lot of that, not because I was incapable or anything like that. It was actually because with a lot of these effects, if you're doing sort of the character screen stuff, you can't draw characters outside the borders. You have to draw them with sprites, which are sort of these movable object blocks. And that means for a lot of effects, you actually have to do, if you want them drawn on the whole screen, you basically have to do one version of the effect for the character area and another version of the effect for the sprites. And in 4K, that's not really that feasible, so I kind of stayed away from that. Yeah, it was released in 1982, the original version. I think the later one came out in 87, maybe 86 or something, with a case redesign to look more like the Amigas. This is just a bunch of the different models. These basically look like the ones that I was showing you. These two don't really look any different. This was a C64G, one that was only released in Germany. I really like the look of it because it's like got the sort of grayish keys, but still the old case design. I think that's pretty cool. In terms of the audio and video, so the video I kind of covered with like how big the resolution is. There's 16 fixed colors. This is something I really should have in a slide because I actually love the palette here. Just gonna pull this up. Here's a pretty good representation of it, and in order. So here's the color palette. These are the 16 colors you have. They're more or less just kind of arbitrarily chosen by the chip designers. Like they just kind of thought these were nice colors, I guess. And when you see it on a real system, they're usually a bit brighter, kind of blown out, and a lot more saturated. So yeah, this is a pretty nice version of it. But typically it ends up being a little more intense than that, I think. By the way, hi to guys in the chat. Local hoster Rep Nop, Dark Second, Soul Threads, Wister Tobe, Dur2. How's it going, guys? And then the OS it has what's called the kernel with AL. By the way, hey Hoffman. Hoffman did the music for this intro, by the way, as he always does, because it is a Logicoma thing. We will watch this in a sec, but I kind of want to go over the hardware itself before we do that, because it's more fun to sort of keep that in mind, because I kind of want to get across how difficult this is. For those of you who aren't familiar with the system. For those of you who are familiar with the system, then you already know, but you know. In terms of what the OS gives us, basically nothing of value when we're doing this kind of demo. There's a little bit there that we use for table generation in the basic interpreter right at the beginning of the demo. But for now, it's just, basically the first thing we do is, other than that table generation, we just bank those out so we can get the memory behind them, because the CPU can only address 64K of memory. So to actually like do the kernel and the basic stuff, part of the memory is actually banked into ROM. So if you access that, you'll get the ROM. Unless you write to it, then you always write to RAM. But yeah, so just to actually get the full 64K, we need to bank those out and then never touch them. But that's actually an advantage anyway, because then that also frees up all the other memory that the system uses for variables and state and all that kind of stuff. And then we just get to use that for whatever we want. We get full control of the computer. And that's basically what we do. So I think that's basically all I wanted to talk about the system beforehand. And now let's watch the demo. I'm just going to run it in the emulator here and we'll do a quick pack so it won't actually be. By the way, this demo, it was in we got second place in the combined intro competition at Soul School this last weekend. Super happy about that. Second place to a really cool Fairlight PC 4K. The file size of this was exactly 4,095 bytes, but I'm about to pack it in the instant mode, which is a quicker version of this packer that I made, and then we'll talk about that later. So it's going to be a little bit bigger when we watch this, but it really doesn't matter. And the last thing I'm going to do is, I'm actually going to keep this size. This emulator, by the way, this is Vice. Very, very good emulator. Absolutely integral to this process. But yeah, I'll shut up and we can watch this. I'll even mute myself here. By the way, this is actually when it's generating tables. But there's kind of this tradition to clear the screen with some effect before the demo starts. I really like that. So that is Makeshift. By the way, I totally forgot to watch this in the more fancy debugger where you can watch the memory, but we'll do that later because there's some really cool things about how I was able to get the fast pacing, where basically one effect has to be loaded while another one is showing, and I'll talk about that later, so we'll probably watch that anyway. But anyway, thanks for the kind words, guys. Hoffman obviously did a phenomenal job on the music. Super happy with that. It was his first time he'd done anything with the SID in like 20 years. Like literally, I think it was 19 years ago he did his last SID tune. Pretty crazy. And what I personally love about this is that it's really technical. Like this is probably one of the more technical things I've maybe ever done. It's on a small enough scale that it maybe like it didn't feel like the hardest project I've ever done, but it was like everything here pretty much is done by us except the music player, which was done by Format of 8-bit, and I can't remember his other groups, but lots of other groups. And yeah, so basically this project started with that plasma effect. So let me kind of pull that up. If I can just pull that up in isolation, which I think I should be able to do with the Zoom plasma. We should have a version of that here. Test tune and some other stuff. And this is actually okay, no, this is basically the same version. Yeah, so this is basically I started with this effect. And how that started is, so I've wanted to do C64 for quite a long time, and it was sometime around 2011, I basically learned, maybe a little earlier than that, I learned how much of this stuff actually has to do with tricking the hardware and not just like writing really fast CPU code. For example, this effect actually does some X stuff with some really fast CPU code, but then it does this Y stretching stuff with a hardware trick. And so yeah, back in like 2011, I wanted to learn how a lot of these worked. And so I went through Edge of Disgrace in particular, and I went in Vice and I saved out, like I just went into certain effects and then would save out save states for all these different effects. Particularly, I can actually probably pull this up, these snapshots here. I actually did, I have a repo here, let me link that, where sometime, like I basically didn't dig into these save states until a few years later, and I don't really know why I didn't look into them around when I grabbed them. But I've just been sitting on them for years. And sometime this last November, I got into this again and just sort of started diving into watching a bunch of these demos. And in particular, I thought, okay, maybe now's the time for me to actually dig into the technical details here. So the first one I dug into was the Char plasma with sprite zoomer on top. And it's basically the plasma in Edge of Disgrace that looks a lot like this one. The innovative one with this one, of course, with my implementation, is that it doesn't have another effect on top of it, but instead it's zooming. And I didn't want to claim this in the intro, but this is the first one that does the full character screen that actually zooms. And I have not seen that anywhere else. If you guys have, please let me know where that is. But I totally hadn't seen it, and that's kind of what made me really excited about this, was it was like, okay, I can finally innovate with something here, even if it was sort of a incremental change like that. Anyway, with this Edge of Disgrace plasma, I sat down and I just started digging in the monitor. So Vice is not only an emulator. If you hit Alt-M, you get like a memory viewer, and you get a monitor here. This, by the way, is totally what inspired me to start with a monitor when doing Rush Jewel Boy. Was working with this. So you just get a console here, and you can, honestly, I don't remember most of the commands in here. You can do things like watch registers, go until those change. You can see this is scanning out the plasma on the top of the screen here. And basically that kind of stuff. And just from doing that and just sitting there and like trying to figure out all these hardware tricks, I just wrote down everything I could find about this stuff. I wrote down what I thought the memory locations were doing. I went through and I found the initial raster IRQ. I looked at the IO regs when it started. I looked at like so much stuff here. And finally I ended up figuring out basically how it works. Now there's a lot of details here that aren't terribly important, because I didn't know what was important, so I just grabbed like all of this. By the way, I got to show you the cooler C64 debugger that came out recently. In fact, why don't I just pull that up now, because it's pretty cool. I didn't actually use this tool very much while making the demo, and it was because I think the new version just came out like 2 weeks ago. and I didn't feel comfortable sitting down and playing with it too much, but I did use it when doing the effect sequencing because I just kept getting crashes and I wanted to see the memory. But this is a sick tool. Let me pull this up. Now, this is a C64 debugger. It looks like a scene straight out of a 90s hacker movie. If I hit F9, I can load... Okay, so we already have the right disk image here, which is the disk for the demo. And what I'm going to do is I'm just going to go over here. This is the sort of emulated C64. And I'm just going to type in load *81, which is going to load the first file on the disk in drive 8 as binary. I'm going to hit enter, and you're going to see it searching. And now here, it's actually loading the intro here, loading the demo. So a little tour of this, by the way. We have the memory viewer here. This is also a memory viewer. These are also memory viewers, and this is disassembly of what the code's of the code that's running. Here you have register values, and you also have like raster positions, and then here you have the emulated screen. This has a lot of screens in it, actually, most of which I don't really know my way around this tool that well yet, but this one's particularly useful for breaking this stuff down. And honestly, I would have loved to have had this 6 months ago, but I didn't. So anyway, it's pretty sick. I really need to embrace this more. Ended up sitting down with a couple other coders, Emun included, at Solskogen and started breaking down some other effects, and it's totally going to use this moving forward because this is definitely not going to be my last C64 demo. Anyway, now that I have this up, I kind of actually just want to watch this again and kind of show you guys a little bit of what's going on when the demo runs. So I'm going to type run. First thing that just happened is it relocated itself here, then it decompressed. Now it is done decompressing and it starts generating this table. So it's generating this table into this memory here, and it's generating one sine wave. That's not what this is, by the way. This is the character set for the plasma. It's generating one sine wave, and it's also clearing the screen data and the color data. Uses that first sine table to generate all the other sine tables by doing some shifts and some adds to it. And then finally the demo starts. And this is pretty crazy. So the purple stuff you see here is writes that happen. And the writes you see here are actually, it's unloading the plasma. So it basically unpacked the plasma. So it did a decompression stage, and I'll get into this in more detail as well. But then it sort of unrolled a bunch of loops and prepared a bunch of data here so that instantly when it wants to switch, it can just switch over to the next effect. And then the blue stuff is stuff that's being read. So this is actually a big unrolled loop that's being executed that's doing the Y stretching here. And the X stretching is stretching into the memory down here. You can actually even see the sort of plasma pattern there closely. Yeah, Drew, totally. That's there was another tool that I'd seen that done that, or that did that. But yeah, this is exactly the same interface there. Sorry. I had the music a little loud, but yeah, I mean, it's just kind of cool to watch this. And like whenever you see an effect is going on, you'll see more unpacking going on down here. I think the next stage is already done though. And this one, you'll see a lot of like flashing, and it's because there's actually a lot of sort of scheduling that happens. Like every 16 frames, we have to shift a bunch of memory and a bunch of stuff. I'll get to all this in the individual effects. But yeah. So here it's reading out different lines of the scrolling picture. That's what these blue parts are. The purple parts here is where it's writing the next lines of the sprites as they're scrolling up, because we can't do it all at once because it's too slow, so we have to do it, yeah, all that stuff. I did not write this, and I did not write this tool, and the whole demo itself is written in Assembler and Makefiles, including the music. There's no tool for the music. So Hoffman had some fun there. Nah, the demo is all done in Assembler. Yeah. So after showing that, I kind of want to talk about some of the unpacking stuff, and then I want to kind of go into the effects. But right before I do, I want to finish that thought I had earlier, which is basically that, yeah, this whole thing started again with with this plasma effect because I basically had figured out how it was going to work. And sitting down in Rust, I prototyped the whole thing, and I'll pull that up in a minute as well. And then I just kind of sat on it for a while, just thinking, okay, next time I kind of get really stoked on C64, I'll just kind of make this into an effect. And yeah. Then sometime a few months later, I think it was after revision, like shortly after revision, I was working on our 64K packer, and I just kind of thought like, man, I haven't actually done a 4K in like 5 years. But if I come up with an idea, I totally want to do one. And I sat there thinking like, I actually have an idea for one effect, but it's this C64 effect idea, because it was, once I learned how the Edge of Disgrace one worked, I realized, oh, that can totally be used for zooming, I bet. And like at that point, I had most of the prototypes, so I adjusted the prototype a bit more to be a little more accurate. And then within like a weekend, I had a long weekend. I can't remember why. Oh yeah, it's because our the team I was on at work just released our 1.0, so we had a long weekend after that, and I spent it porting this effect to assembler, and it totally worked. And then as soon as we had that, this would have been in late May or so, or mid May maybe. Then it was like, okay, since this is the first one of these effects that I've seen, we need to put it out. And it would totally probably work as a 4K. And so my plan was to have Hoffman do a SID, and like normally a SID player with music and sound and the player and everything is about 2.5K. So it's like, okay, if I can get this down to around 1K and we have about 2.5K for sound, then we have, okay, like 3.5K, do some text stuff and some sync between those, and then we have a pretty decent 4K intro. But then Hoffman contacted Format, and Format's like, hey, I have this player that I made for this kind of stuff, where you'll do the music and the player in 1K rather than 2.5. And so then once we had that and we got the driver working, that was like, okay, then I need more effects. So the next one I did, I looked at a bunch of other demos, and I saw a demo called The Concert by a group called Performers that does that sort of layers effect. And I'll probably pull that up later as well when we look at that. And I just fell in love with how that looked. And so I was like, okay, got to do that one. And then I got that working, and it ended up being really big. But I also thought, okay, we'll do those two, and then we'll do an alternate version of this that I had where I sort of replaced some of the math, and it looked a bit different. I'll show that as well. And then I just looked through some other effects that I had, and I had that sign boxes effects, and then, yeah, okay, so now we had the effects. It ended up being that it was all like 5K or something, and I had to get all that down, but yeah, we'll get to that when we get to some of the individual effects and how they fit together. But yeah, so that's kind of the story about this intro, is like, it started with me figuring out how the Plasma and Edge of Disgrace works, and then realizing I could do it with zooming, and then wanting to get that out once it worked. And I think it was just super fun. Like, I was a little bit stressed sort of late last week before the party started, but I just kind of chugged through it and just got a lot done those last couple days before the party. And then at the party, I just had a blast, just hanging out with people. And I mean, I was coding the whole time, but it was really fun, like half coding, half social. Anyway, a little bit about how, actually, why don't we just dive into the effects? Let's do that. I'm not really sure how I want to present this because kind of went all at once. But yeah, so this is the Plasma, and this was sort of the main thing we made. As you can see, this version's a little bit different than the one that's in the demo. The colors are the same, the motion is mostly the same, but we have some variation in the motion in the actual demo. But we have these little like top and bottom border pieces here, and it's just literally aesthetics, nothing to that. Although it's kind of annoying with the timing that this effect requires to actually make that, so it was a little bit fancier. I ended up cutting this for size. But the code here ends up being really simple. So basically what's going on for this top and bottom border stuff is, this is really common in C64, is like you're really tied to what's going on with the actual raster. So rather than actually writing pixels to a frame buffer most of the time, you'll like wait to a certain scanline position, change the background color, and then that's what'll give you like this line. And then one scan line later, you'll change it back to black, and then you'll get this. Interestingly enough, these lines are actually within the top and bottom borders. I actually disable the top and bottom borders down here, and then change the background color to get this, and there's some other caveats there, but I'm going to skip over a lot of that stuff. But the effect itself is a little more complicated than that, and to show some of that, I need to pull up the prototype. So the prototype is something where I basically emulated just enough of the system, not like a CPU emulator and not like that low level emulation, but just like a high level, like, okay, I kind of know that this is how the character memory has to work. And if I get that, then I can do some hardware trickery to do the Y stuff. So I kind of just emulated that happening. So basically, let me see if I have it's probably in here in Zoom Plasma. And we should have Plasma Test. Let's see what this looks like right now. Okay, so this looks like crap. This was an older color scheme I was playing with, and as I was doing the motion for this, I was also playing with simplifying some things. So this looks a bit different. But this will be enough to be able to show off what I need to show off to show you how the effect works. Let me pull up some of the code here. So yeah, so this whole thing's done in assembler with make files. And so this basically what I would do is I would develop an effect in isolation like this, mostly in the prototype first, and then bring that out into assembler in its own little standalone project. And then I would sort of move that into the framework. Now, because this was the first one, this one kind of became the framework. And there's a couple bits that are used by other pieces as well to like unroll code and stuff, because all that has to become procedural and very small. So like the 6502 is unrolling its own loops as it's loading. I think I need to slow some of this down for the parameters here. The other thing I was doing with Rust, once I have all this stuff in the prototype, then I have a lot of the data sort of already prepared. And so once I have that, then I'll use it to sort of spit out the data. And so there's a process there too, where it's like I'll make the prototype and I'll do, here, let me just turn down a lot of these here. I think that'll make it bearable to watch. Yeah, kind of losing my train of thought here. Anyway, so I would kind of do the prototype first and I would do it really informed about how I knew it would work. Like this looks pretty chunky, not a very smooth plasma, but that's kind of, how it was. So there's basically two parts to this. The first one is the X part. So for those of you guys who may not be that familiar with a plasma generally, the sort of math here that gives you this kind of pattern is that you have the X and the Y position on the screen. So let me just pseudocode this. So you have X and Y as your sort of inputs here. And what you're basically going to do is you're going to take sine of X plus sine of Y, and then you're going to put sine out here. And with a bunch of different like constants in here, and also adding like time in here and time in here, and then just adding constants to this, you basically get that pattern already just on its own. So that's what this is. Now, the way we actually make that happen, because we don't have near enough CPU to do like everything per pixel. In fact, let me do some sort of back of the paper math, back of the napkin. This is my napkin. Let's say we're able to do like the basic 6502 code for 1 pixel. It would be something like we need to do something like calculate this. So let's say this was a table lookup, this was a table lookup, and this was a table lookup. So in total, we'd have like, I'm being really generous here, by the way. This is going to be a very low estimate. But let's say we had like 12 cycles to do these 3 lookups. And then in addition, we had to like shift that into the color and store it, right? So we say like, okay, 16, 12 to 16 cycles per pixel. The problem is we have 160 because it's a half width mode by 200 pixels. This is how many we need. Times 16 or so cycles per pixel, and we have 512,000 pixels or cycles that we would need to do that. Now the problem is we only have about 19,000 cycles per frame, and so clearly this is not going to work. Let's see, we do 19. Actually, I'll do the scientific one. Divided by 512,000. We need. We have 3% of the CPU that we would need to do that, which is pretty ridiculous. So the short answer is pre-calc and being very clever. So let me show you kind of how we break this down. Yeah, here's, by the way, kind of how I do this informed. I kind of sort of write how I think the assembler is going to look while I'm doing this stuff. But I need to show you a debug view here in this little prototype. So basically, I think this one's going to give us the simplest view, which is what we want. Yeah, so this is the simplest view. Do we have one? Yeah, the lines repeated. This is what we want to see. By the way, this is just like straight up Rust with mini FB. I'm totally going to release source for this, by the way. I want to do the note. So a note, by the way, is another C64 tradition. The note is kind of like a README, but usually goes into a lot of technical details, and it's presented as an actual like program on the hardware, so that you like it plays music and you have like the border around stuff and you get the text and you hit spacebar and it'll go to the next page of text. Really, really great tradition. I'm totally doing one of those, but a bunch of stuff piled up this week, so I haven't had a chance to put that out. But I'm going to put that out this weekend, and when I do that, I'm also going to put out the source. So bear with me for that. But yeah. So if we take those two parts of the plasma, let's see. You know, I might actually just make a new project for showing this actually, to kind of show you guys. That might take too much time. I'll just roll with it. Let me just dig in here, and we'll do. Actually, this one we want to set to 0, and then when I do this, that, yeah, there we go. So what this is here, this is a bunch of like debug views that I made while making this. So what this is showing you here, this is if you take sine of y, and then you get a number from 0 to 3, and then you look that up with a certain like set of colors. In particular, I can make this. Actually, I think I did it like this, where if I hit up and down, it'll cycle through a bunch of color combinations that I did. A lot of these are taken from Edge of Disgrace in order for me to sort of test, because I spent a lot of time kind of. Once I figured out technically how it worked, I still wanted to figure out how to generate the data set. So I played around with a lot of those palettes as well. Although like none of those made it into the actual intro. But yeah, so this is just like sine of y. Now what we want to do is we want to bake as much as we can into a character set. So what we're going to do is we're going to generate a character set. So the C64 is basically going to display character graphics in this tiled mode. Where the whole screen is going to be split up into 8x8 tiles. They're technically 4x8 tiles because this is a 4-color mode, so all the pixels are going to be double wide. This really dumb caveat of the C64, but it gives it a really characteristic look. So we basically have, in a character set, you have 256 of these, possible tiles, and that takes up 2 kilobytes of space. And so literally what that is you have all the data for the different tiles. So you'll have data for tile 1, and you'll have the first line, the second line, up to 8 lines, each as 1 byte. So it's 8 bytes per tile. And again, 256 of those. So each one of those is basically going to represent, we want it to represent sort of a sine wave that goes through that. So we're basically going to bake our sine of x and our sine of y in this way. So what we're kind of going to do here, how do I sort of explain this? Did I erase that pseudocode I had? Let's get that back if we can. Yeah. What we're going to try to do is basically bake this. I can't remember which identity that I take advantage of for this. But we end up baking it something like, we bake this part. I can't remember how this fits together exactly anymore, to be honest. But anyway, I'm just gonna roll with this. We're gonna bake it so that, let's see if I can just show this. Oh, need to do my debugging stuff again. So you saw that was sort of sine of y. We're going to bake this so it's something like sine of x plus y. And right now we're still getting some scale stuff. So let me go ahead and remove that basically. And we'll remove the y move stuff. And we'll remove the flow stuff. I'll probably have to simplify a lot of this to show you, but that's totally okay. Here, we'll remove the flow. And then we should get this. So what I've done here is basically I went 2 steps ahead of where we were. So I have every 4th tile represent, like if you put all the 4th tiles just in a row, you would sort of get this wave pattern that just looks like sort of one cycle of a sine here. So it's basically sine of y plus x, if that makes sense, and you'll get that kind of pattern. Now the reason I do every 4th is because not only do I want to be able to just display that wave, I want to be able to display that wave sort of shifted by up to 4 pixels. Because as soon as you shift up to 4 pixels, then it actually looks the same as it did before. It's just all shifted 1 tile to the left. So the intermediate tiles are filled with shifted versions of each tile. And so then by just changing the tile indexes for every line here, so for every like x position here, we just change the tile index, we're able to get this sort of pattern here, where we have, so I use a table to give like a starting index, and then I add 4 to that basically as we do a running total. And that gives us this kind of pattern. So we're able to sort of have the shifted sinus just like this. Yeah, all in sort of pre-calc data. Now, of course, if we were to display this on the system, we would have to fill in 40 by 25. We would still have to fill in 1,000 characters worth of data, but at least we would only have to calculate what the character index is per vertical column. So we would only have to do that 40 times, but then we have to fill it in the whole screen. We don't actually do that, as it turns out. But before I move on to that, there's one more step to this, which is how we do this sort of scaling. So when you do a zoomer, not only do you need to do this kind of running total, but instead of jumping every, like, so if I jump every 4th tile, if I jump 4 tile positions every, if I increase my tile index by 4 for every character position here, then I get this nice wave here. But if I instead increment it by like 5, the tile index by like 5, then I'll actually jump a little bit past the wave. And if I do it a little bit less, then I'll jump like not quite to the next tile. And if you do that, something really nice happens. And the answer is you get scaling. And when it really kind of scrunches up, you can kind of start seeing aliasing. Because you can sort of see, I can't actually point at this, but you can sort of see where like the tile boundaries are. And then, yeah, it can go pretty wide as well. And you also see some kind of like, they look like duplicated pixels as it stretches really wide. But literally all we're doing here is we're taking a 16-bit value, and I use a 16-bit value because we need to do fractional bits when we do this. Like if we just jump 4 or 5 in our tile index, that's not going to be accurate enough. We need to jump like 4.1 or 4.2 and get in sort of that range. And we can't actually do that because there's no floating point processor in this hardware, but we can represent the whole thing as a 16-bit number, and then we just take the upper 8 bits for our tile index, and the lower bits are just for adding in our sum so that we actually get some fractional bits in our high stuff. So basically, I have a sine table that's saying where does that start, and then I have another one that offsets that by what our scale value is. And then I just do this running total, how much to add to the tile index every time, and we get this. So that's sort of how the X part of the plasma works. And except for one caveat. So that's if I display that for the entire screen. But what I actually do on the hardware is I only display one row of characters. So if I do that, so all I've done is I just don't display the rest. But this is the exact same data you just saw. But this is more accurate for what's actually happening on the hardware. So what's going on here is I only fill in these first 40 character indices to do this first row. Then to create the plasma, I use a hardware trick that at a very high level will, as the screen scans down to actually like send the signal to the TV as the raster scans, as we would say, I do some mean stuff to the hardware to mess up its internal counters. And what it allows me to do is to select which of these. So like if you think of this as a 160 by 8 picture, for every scan line, we can actually choose which of those 8 scan lines in the original picture that we actually want to display as the screen scanning down. Does that make any sense? Let me go ahead and display the whole thing again. And maybe this will start making some sense. But basically, this is just the whole thing as a zoomer. But it's the same thing. If you were to cover up, let me do this with this other window. If you cover up the first little bit here, it doesn't look quite the same because of the way that I'm doing still scaling in the Y. Let me turn off the scaling and then we'll just get the movement. In fact, I can also turn off the Y movement here, which is actually already off. So what this will look like is this. So we just have sort of this one plasma picture that's moving left and right. But if I just show you this first part, it looks exactly like those original characters. And if I were to show you just more scan lines, you could sit there in Photoshop, and I did this with Edge of Disgrace to see if this is how the data was laid out. If you look at it, you can actually like start picking out unique scan lines, and you'll see that there's only 8. And it's actually really weird because it looks like there's a lot more unique sort of scan lines in this picture than 8. But what we do is we select them. Like if you remember this picture I just showed you, where it was basically the lines displayed the entire height of the screen. That's what would happen if we just picked, from this original picture, if we just picked the first line and then the second line and then the third line until we get to 8. And then for the 9th line, we just do the first line again and we just repeat that the whole time. Then you'll get this same pattern all the way down. Now, the interesting thing is if you do that, but instead of just picking that same one, if you add a sinus to that, you actually get this plasma effect, and that's the whole thing. So we sort of pre-calculate this X stuff. We pre-calculate a character set for this X stuff, and then we pick tile indices based on this X scaling and X movement. And for then the Y stuff, we're able to pick which one of those scan lines we choose, again, based on some offset when we scale, and then we do another sinus pattern in there, and we get this pattern. It's kind of mindfucky, but it's actually a lot simpler than I think it sounds when you sit down and kind of think about it. So this is with sort of no motion, and you'll just get a static picture. But it's still looking up, in the X stuff, it's still using a sinus because that's baked into our character set. And in the Y stuff, it's still using a sinus to display the lines. Now, if I add some X move stuff, then all we're doing is we're offsetting the running total that selects the character, the tile indices, and then we get this, so it moves smoothly back and forth, and it will repeat after basically 64 tiles. And then the Y stuff, it just offsets which scan line we're selecting, just offsets that selection. So we'll get this sort of panning shot here. And then we have the scaling, and that's basically using a couple tables to affect where do we start in our scan line and tile selection, and how much do we add to our running totals to actually like look up into the tables and then select. And the final thing we have is flow, and this is where it really starts to kind of sell the effect. So this is just with X flow, but I'm not actually seeing it. I'm pretty sure I disabled that. Yeah, here. So with the X flow, something interesting happens. In fact, let me turn off the scaling so you can sort of see this a little better. And let me actually turn off the movement as well. But all I'm actually doing here is instead of like stepping a constant value in my tile indices, I do that, but then I use that as sort of a table lookup into another sinus table. So I basically take the tile index I should have had, and then I add some sine value that's my X position plus time, and you get this kind of flowing motion here. So it kind of stretches and then doesn't stretch. So you can kind of see the sinus pattern here. So it's like really stretched, and then it kind of smooths out for a little while, and then it'll sort of stretch again. It's just adding time to an index in this table. And then we do exactly the same thing with the Y, where we just select different lines based on another sign table. And here we start really sort of getting that flowy look, or that really plasmatic look. Most full screen plasmas on C64 you'll see will look a lot like this because they often don't have the X motion. But it's when you put them together that you actually get a really sort of convincing effect. So you get kind of stretching in the Y and in the X. And this isn't zooming yet. This is just doing the plasma. And then when you mix that with some movement, so now it'll move in X and Y as well, which again is just offsets. Then we start getting something kind of nice. And most like the full screen plasmas and Edge of Disgrace look like that basically. And then most of them, of course. There's a couple that don't. And then we get the zooming, which is what's unique about mine. And it may be a bit kind of hard to visualize some of this, but those are sort of all the different pieces. So basically all we have to do every frame is we have to set the tile indices of like basically those select which lines we have to pick from. And then every scan line as the hardware is displaying the screen, we have to basically change which line, select which line is actually showing. Now, in the actual C64 version of this, it gets a little complicated. So let me do, this is the one in Makeshift. So we'll do, I wonder if it's easier if I hack the other one, actually. If I just hack the standalone one, because then it's, less loading time and stuff, because we don't have the, although it's actually slightly different plasma there. I'll do the one in Makeshift. Do the one in the intro, which means we'll have to skip over some loading stuff, but that's fine because we have zoom mode. So the version of the plasma in the demo now doesn't run standalone anymore because it's like it relies on some bootstrapping stuff that's actually in the intro. So I'm just gonna make this, and it just built everything and put it in the emulator, and then I can do Alt W, which will give me warp mode, and then we can skip a bunch of stuff. But I'll hack it so that we can skip the intro part here. So I'll go into intro.asm, and somewhere down here, we'll just go ahead and instead of initializing the text stuff, we'll just initialize the plasma stuff, and then we'll skip this background thread, which is loading other effects later, and we'll just, loop. So we still have to let it generate the table, but here we go. Right, so this is what the effect actually looks like in the intro, and it's a little bit different because we have these different color changes and also different movement changes. But all that's actually doing is it just like we have those variables for the flow index and those kind of things, and all it does is just every like 22 by 8 frames, I think it was, which matches the timing of the music, and then we just load up another set of values, another set of colors, and eventually it'll crash because it will try to jump to the next effect, but the next effect isn't ready because we just commented out the loading for it. I can actually just comment that out as well. If I look for cycle here, actually it'll be this one. You just do this, and then so now it'll just keep running the same thing over and over. I think it may actually do some weird stuff because of the way I did the sync was designed to be really small, so there may be some weird stuff here. If we let this run for a bit, I'm actually kind of curious. Okay, it's actually not that bad. But yeah, we're going to start getting a lot of zooming. Because I actually just increment the zoom speed every time it shows the plasma. And then, it's going to get pretty large, I would imagine. Kind of funny. But so if I can kind of break some of this down, I can't go over too much of the code in detail because it's a big wall of assembler, but there's pretty distinct parts here. So the first bit of code here is basically unloading stuff. So this is going to happen in the background of the text effect. The text is sort of moving up and down for the title of the demo. It's going to initialize a bunch of its variables. It's going to unpack its character set into a specific place in memory. In fact, I skipped over a really big detail here, which is with this hardware trick that I'm using, the memory has to be laid out in a very specific way. And I kind of skimmed over that because it just makes it more confusing, even though it makes it work. because it's not actually true that we can select one of those 8 lines that we made earlier. We actually have to change which character set we're using, and then we lay out the character sets, a bunch of different character sets that represent the same tiles but different scan lines of the same tiles. And by changing the character set index, we actually pick which line it is, even though that's technically not what happens. But basically, all of this is sort of generating that, and then it unrolls one of the loops, which is the, like, when it does the hardware tricks for the Y stuff, we actually have to have a loop that sits there and hits on this one register every scan line, which will adjust its counters in such a way that it will do this weird stuff. And yeah, that has to be very timing critical. It ended up being, I think, in the end that I didn't have to do this way. I could have just done it as a loop, but I think it ended up being smaller to keep it as speed code, and of course it's a lot faster to do this. So this is just generating a big old unrolled loop from a little template that we have that represents the body of the loop. So there's a template, and then we go and update one of the bytes of the template, and then copy it, and then update it, and copy it, and update, and copy it. It's pretty funny. Drew2, Ferris, you got your old school ASM on for this demo. I thought you were done with that and had moved on to generating ASM with high-level languages. Was it cool to get back straight into straight ASM again? It was really fun. And even here, like starting out, like this unrolled loop, this has to be unrolled by the code itself now in order for it to be small enough for the 4K. And that's generally something that's really common in C64 anyway, because even if you're doing a larger demo that's loading parts from disk, like in this one, we generate a lot of the data and unpack a lot of the data behind other effects. And that's really analogous to what the larger demos will do, which is they'll load them from disk. And even when you're loading from disk, the disk transfer is so slow that you'll often do a lot of these kind of compression techniques. So that usually it's the same kind of thing. But the other benefit is like we get this big unrolled loop and it's really fast. But initially, this assembler that I use, it's called Kick Assembler. It has a little macro language, so we can actually, instead of like unrolling this loop, we could have done something like for var I is 0, I is less than, I think it was 198 lines that we do, I plus plus, and then whatever you assemble in here gets repeated that many times. So in prototyping, of course, I did a lot of that, but then I had to sort of translate it into this generated stuff as well, which ends up being pretty mechanical. It's a lot easier than it sounds like, I think. Yeah, see you later, Hoffman. But yeah. So then we get, that's the first stage of the init, and the second stage of the init will set up the different interrupts that we actually need to do so that this effect will run rather than a different effect. And then we get to our frame, and so what it's going to do, it's going to set a bunch of registers so that we have so that the hardware is pointed to the right places in memory and all that kind of stuff. We update the music, set up the background colors and everything. You can see a little bit of scripting here already because we take this cycle counter, which is how many parts of the music we've seen in this effect, and then basically using that as a table index here to store colors into these registers. Now again, we only actually set that first row of characters, so we only have to set the first row of color memory as well, which ends up being we use 2, I think, different colors for the color memory. So in order to get the different palettes down, like the different color sets I use for this effect, in order to get those down in size, I only use 2 sets of colors for the plasma effect, and it alternates between the 2. And both of them have the same, so there's 4 colors, and only the darker colors actually change between those sets. So the higher colors are the same, and then the darker ones are actually different. So these are the high colors here that are the same, and then the other ones are going to be the dark colors and the char colors there. There's a couple more things about taking that cycle counter and then loading those into the flow stuff, which will also change the movement of the plasma. I think the X offset and Y offset just continue from where they were, and then the zoom stuff, I'm pretty sure I offset the zoom and then add 1 to its increment variable or whatever. Venn Gam design, not gonna say that. Hey, Middle Voids. Yeah, that's probably where I took that from. Is from Kick Assembler's thing. It's really nice. But basically, then this is going to, update all the indices that it uses for the effects. Just straight up adds. Hey, Tomko. And then here's where we do our what I call the X update, which is basically setting those character indices. So again, it's just a very basic 16-bit running total. Initially, I also had this as an unrolled loop, but it ended up being smaller to not do that, and it's totally fast enough. Sorry, ion codes. But yeah, so this will update the character indices. I wonder if I can get a version of this where I don't do the stretching, but I just do the character indices. Because there's some kind of funny stuff that happens when I do this in the actual assembler version. I think the best way... Actually, I can just not call the stretching loop. Yeah, I'll do that. So we'll go here. There's a bunch of stuff happening here that I would love to talk about, but I might have to skim over. Where does it jump to the stretching loop? Here. Yeah, so this is what it looks like when you don't actually do the stretching stuff. And there's some kind of weird stuff going on here, why it looks like that. Or is there more to this? Should be fine. Shouldn't cause us any problems. I think that's okay. Yeah, I'll put this back, but then I'll do like the wrong values or something. Or I'll make it miss the timing window. If I go into... There's a loop here. This unrolled loop actually has to be a specific number of cycles. If it's more or less, we actually lose the effect, which should be what this does. Okay, now there we still get it, but we're a little early, and so some of that messes up. Let's add more no ops here. Yeah, that's actually too many, and then we go over the screen. Let's see if I can just remove a bunch of these. So there's a lot of kind of weird stuff that has to happen for this to work. Basically, this is what it looks like if we don't do the stretching, but we have the right sort of character pointers. So I'm skipping over a lot of details, which kind of makes a lot of this hard to justify and explain, actually. The way that the character sets are laid out, they actually take up an entire 16 kilobyte region of memory. Now, the hardware on the C64 can only see 16 kilobytes of memory at a given time. And if we use 8 character sets, we fill up all that, which means we don't actually have enough space to store the map, which is where all the character indices are either. But what's interesting about the hardware is it will load a bunch of data into internal buffers, and then if you can sort of trick it to never read those buffers again, which is kind of the main trick that we use here, then you can do weird stuff. So for example, I actually have the VIC looking at a different 16 kilobyte chunk when it starts out, and then it reads in the screen memory from down there. And then before it starts displaying this area, I quickly switch the bank to a different bank where all the characters are. And then I basically have it repeat the same character line over and over again. And then by switching the character set every line, we're able to get sort of different lines of graphics data. So yeah, again, a bit confusing, but kind of just to show you what that code looks like. And yeah. This is in a macro because it has to be actually used in 2 places. It's used in the unrolled code, and it's also used right before to figure out what the character index for the first line is going to be. So yeah. Now this was the second most technical effect in the demo. The most technical one actually ended up being the layers effect, just because of so much scheduling. This is really just kind of a hardware trick. For those curious, it's called what was it called? Flexible pixel position with the last line of the character. And if you're really curious about how the C64 works, you can go Google that and actually figure out how this trick works. But yeah, I think I need to stop talking about it because it's been like an hour already. Haven't even gotten through the first effect. There's a couple things that have to be done though that I also want to convey here. In order to do that loop and to trick the hardware like we're doing, we have to write to this register on every scan line and on a specific position within that scan line. Shut up, Tomko. And so to do that, we actually have to synchronize the CPU with the raster. Now it turns out in this particular effect, the window that we have every scan line is actually not cycle accurate. We actually have, I think, like a 5 cycle window or something. I think it might even be more than that, where it's basically past a certain point on the line we need to update one of the counters, but we can't do it too late, but yeah, past a certain point in the line. My guideline is somewhere around cycle 35 to 37, and I adjusted that timing a lot as I would do like different border stuff and things, and it didn't really matter. So I actually end up doing a trick that gives us, synchronizes us to the raster position within 0 or 1 cycles of where we would expect it to be. And so that ends up being enough for this, and then we just have to like wait enough cycles until we start doing that loop. And then that loop has to be exactly as many cycles as it would take per scan line. But then it just works, if that makes sense. Yeah, Dura 2, it's slower and makes you thirsty, absolutely. So that's more or less how that works. So there's a lot of code here, like the frame interrupt. First thing it does is it calculates the first line here and stores that in a variable, and then it will set up another interrupt that happens later. And that interrupt will set up an interrupt on the line after it, and then make sure that next interrupt happens in a bunch of no-ops. And since no-op is 2 cycles on this CPU, then when this interrupt fires, which is where our stable stuff is, and then we're going to do our screen update loop, our line selecting stretching loop, then we're within 0 or 1 cycles of where we expect to be, which is totally good enough. So we use this sort of multiple raster interrupt thing to sort of do this. It's pretty fun, really standard affair C64 stuff, but yeah, kind of cool to explain. Ion Code says, what are these? These are like local labels, and then when I say, so like bang is a local label, and you can say like bang the label as well, but the bang part means it's local. And if you do this and then a minus, then this refers to this label. So that's what that is. Typically when you see a little loop like this where I'll like load an index register with a value and then just decrement it and then branch here, I'm waiting a certain number of cycles. And when I'm doing this, it's not that terribly accurate. Like I have a watch point set up in the emulator to see when the critical register that I need to write is written, and I can kind of just adjust this until that lines up where I need it to be. Of course, cycle counting on 6502 is actually not that bad. So I do a lot of that in my head, but of course, my point is that you don't actually, like you can be a little bit sloppy there and it's fine. So it's not that crazy. Anyway, that's how this plasma effect works. Pretty cool stuff. I'm proud of having done it, even though it's not the most technical thing, but it's pretty cool. And I do think it's the first full char area zooming plasma, again, that I've seen. Probably not the first just because of how competitive the C64 scene is, but it's the first one that I know of. Anyway, there's the plasma. So that was sort of the first effect. The second effect I did was actually the layers effect, but I kind of want to move on to the boxes effect next to show that first, because it's a bit simpler and it has a couple fun parts, including some stuff that I actually worked on the stream. So change the bootstrapping, so it just jumps into that effect, and we get this. So this effect, I'm just going to pause it here. This effect I wrote, I'm going to pause on a prettier looking frame. There we go. So there's basically 2 effects running here. There's the background wavy character effect, and that's totally the stuff I was working on the stream a couple weeks ago. And then we have this boxes effect. Now this boxes effect I initially wrote when I was about 17. Let me pull up the original version that I wrote then. Now I wrote it for a NTSC machine, and so I did a bunch of things to make it faster. And also I wasn't that good at 6502 back then. So let me pull this up. So this basically had to be interlaced, and I didn't have it double buffered. So yeah, so it had to be interlaced, and it takes a lot more frame time than it should. But when I looked at this, I thought, okay, I really want to have this in the demo. But the problem is that it's kind of boring as is. I would really like to put something behind it. And then I realized if I got this fast enough, I could probably do one of those wavy character things. Now, I actually haven't seen another screen on C64 where they were doing this wavy character effect with another thing on top of it. I've seen ones with better waves than this, but I haven't seen with both of them, and I had to actually work pretty hard to do that, even though the solution ended up being really simple. So what I did is I sat there and optimized this effect. Basically, the way it works is it'll do some sinus stuff and then shift that into a variable, and then it'll do that like 4 times for the left and right sides of the sprites that's updating here. And then, yeah, I ended up getting it so fast that I didn't have to interlace it, and I could do the other effect. But yeah, I actually kind of show this code here. Let's call it sign boxes. There wasn't much prototyping here except for the background stuff, and you guys saw me do a bunch of that on stream. The only difference between that and the product as it is now is that it has proper tiles, and I figured out exactly how the wave would work in that environment, so that it was very easy to port. But this boxes effect, so has to unpack the background characters by like pre-shifting them. That ended up being a disappointingly large amount of code. And then this generates the unrolled loop that will update the background characters. Background characters end up being a lot bigger than the actual effect, which is kind of funny. Yeah, this is a part that sets up all the sprite colors so that we actually get the boxes. Updates the music. Here it updates the sprite positions. And then here we update it was kind of meant to be a plasma. I don't think it's very plasmatic, which is why I call it sign boxes rather than plasma boxes. And it's totally inspired by Edge of Disgrace back then. I wrote this effect, like I said, in like 2009. And let's see. Yeah, so basically the whole thing it does is it's going to load, there's a left and a right sprite to each one of these. And it's going to draw a plasma on the left, and it's going to draw a plasma on the right that kind of has or draw some signy thing. So we go through all the lines here, which is what this is doing. So first it draws out the top part of the sprite, just a few bytes, and then it draws the lower part of the sprite at the end, which is just solid colors. And then it actually does the lines. And so each one, or like the actual lines of the plasma itself, again, I'm just going to call it a plasma, even though that's not really what it is, but that's close enough. So we get this index, which is what gives us the motion over time, and we do some sinus table-y stuff, and then we get a value into our register. And then I end up multiplying that by 4 just to adjust the phase. And then what I did to optimize this is, so I load basically there's 3 bytes per one of these sprites, so 12 pixels for each one. The furthest left is always going to be border, so I load that with A. And then I OR in all the other pixels. Now, the interesting thing is that I was able to, instead of like using the same tables and then ORing and shifting into like the pixels into this accumulator that I have, I can actually just have different versions of the tables that are already pre-shifted. And so then like whenever I'm reading the second pixel, I always read from table 2. Whenever I'm reading the third pixel, I always read from table 3. The other optimization that I did here is, instead of always incrementing this index register whenever I would read a pixel before I read the next one, I can actually just offset my reads by a certain number of bytes. Now, this would cause issues at the end of the table, but then I just make sure that all the tables that I'm using are actually stored twice in a row, so that we get emulate that wrapping behavior. And with all of this, so we just kind of hard code which tables we're reading from for all the different pixels, and it ends up being pretty self-similar and packs pretty well. So we do that for the left side and the right side, and then that ends up being like the whole effect. And again, that ended up being so fast that I was able to do the wavy char thing behind it as well. Now, the char thing behind it, again, is we have this character set that's basically one tile. And originally, I wanted to do 32 by 32. In fact, let me pull up the sprite I drew for that, because I'm actually pretty proud of it. You guys will remember that I drew this on stream, which actually has almost the right palette, but it doesn't do the double wide pixels. I kind of tried to hide that I was working on C64 at the time. I played with another couple ideas here shortly after. So this was sort of the first one I played with. And let me show you the tiled stuff. So this is what it looks like tiled. And I was just kind of trying to get something somewhat unique here. This is a sprite, by the way, which I totally am in love with right now for doing pixel art. So thank you, localhoster, for reminding me about this tool, because it's pretty awesome. And then I drew some really crap things I want to see. This one's called but I think that's something else. Not test Bob. Okay, I don't know where that other file went actually. But anyway, I was doing 32 by 32 because that's what I thought I would get away with. And I made this checker pattern that I really quite like, actually. I'm pretty proud of this. Let me view it, and it's tiled. So I sat down and I found another pattern that looks similar to this. And I started just by drawing an X and then filling in the bits. And I just started, like, I was actually waiting for my laundry to finish one night a couple weeks ago. And I just sat there just sitting there painting this. And it was just like, it was a lot simpler than I think it seems, because I would just sit there and like, here, let me do oh yeah, that's outside of my tiling. Because I would just sit there and kind of like paint a blob and then sit there, oh, this kind of do this. Like it was really basic like that, and I just did that till I didn't hate it. I'm not a genius, guys. I'm an obsessive. But anyway, I did that, and it just kind of worked after I massaged it for a few hours. So that was kind of nice. Pretty proud of that. But then, of course, I realized pretty quickly that if I did this with these with 32 by 32, that's 16 tiles, and 16 by 8 is 128 bytes, and I realized that was going to be too big. So I reduced it to 2 by 2 tiles, and that gives us 32 bytes for the whole thing. And so then I did this one, which was kind of a similar thing, these sort of bobs here. So we can see the tiled mode here. So we get these sort of bobs effect. Again, 4 colors. And that was basically what I was working with. But at some point when I started, so I had this in the demo when it was about 5K. And one of the ways that I thought to get the size down was, okay, what if we use, instead of using 4 colors, because the main thing that I was kind of worried about with 4 colors is that I had to do color ramps for all those to make it fade in and fade out. And that was going to take up a lot of data. So what I did instead was say, okay, let's actually do high res, which will give us either like an opaque or a clear pixel, basically, that will show the background color. And then we'll make the background color be the one thing that we change, and then we'll make the high res stuff be kind of a mask. So then we only actually have to do one color ramp, but the pixel data ends up being the same data. And so for that, we ended up doing, well, yeah, I made this test Bob first. There's a little smiley face. But we ended up doing the Logicoma logo, and I think I just need to pull this up like this. I actually have it here. Brojacoma. Yeah, so this is the Wobble ended up drawing this. And then tiled, it looks something like this. So not quite as fancy, but it totally dropped our data, our size, because we're able to do a couple things. First of all, we only need that one color ramp because we're going to change the background color, and then we make the black pixels opaque. The other thing is that you'll notice basically all the screens in the demo have black. And so when it's generating the sign tables in the beginning, when I first run this, it clears the screen, and it's also clearing the color memory to black, which is how it's able to do this. So it fills the screen with this like full pixel character and then changes the color memory to black, and that's how it does this. It does that at 4 different positions, all offset by 256 bytes, which makes it really convenient to write it out like that. And then as it's doing that, it's filling the color memory with black. And if I just leave black in the color memory throughout the entire demo, that simplifies timing between effects, because then I don't have to have these dummy frames where all I'm doing is updating color memory before it actually jumps into the effect. And it saves space, because then I don't have to store all the code for those dummy frames and all like the states to decide if we're in a dummy frame or in an effect frame. So it became really, really convenient. There's one exception to that, which is when the plasma is showing, we change the color memory to actually show the plasma properly. But that only affects one row, and so then we can just change that back when it moves into the next effect. So that was kind of fun. Really kind of cheeky way to save space, but it was really effective. Like this got really tight. Like I said, at the end we got to like 5K, and I just had to start cutting stuff out, and that really hurt not with this so much, because I could just I could do that. And the other reason why these sign boxes look different is also because I came up with a smaller smaller pattern that still looked pretty good that would do that. And also with the motion, came up with really small ways to just express that in as little stuff as possible. Also, the color ramps here are kind of funny because it's the same ramp up and ramp down no matter what color the end color is. So it just ramps up to like white and then it just changes to like purple or something. Gets this kind of flashy look that actually works out really well for us, but it's really cheap. But again, to save space. And then, so that was that effect. What was I going to say next? Can't remember. I don't think there's much more to say about this effect, actually. It's just that, again, the same thing happens where it like fades in and fades out over these like cycles, I call them, which is like a period of 22x8 frames, and that's what we do all of our sync by. And the color ramps, I end up storing the full ramp, so I store the 4 22x8 byte ramp. But the thing is that it ramps up to 1, which is going to be the white color, and then just stays there the whole time and then ramps down at the end. And doing that, because we're going to run this through a compressor, it ends up being really small because that whole sequence of the ones in there just gets crunched to like nothing. And then we don't have to spend the extra code to sit there and like decide, are we ramping up or are we ramping down? We have to do these compares and like offsets to the index. So it actually simplified that as well. In fact, I think I can show you what that looks like because that should still be using this macro syntax here. So this is the number of cycles in a frame. And of course, we actually divide that by 2 in order to make the ramps even smaller. So it also makes them last twice as long. So they don't just go too fast. And these are the actual end colors it uses. And it was when I was playing with that I had the idea to sync it and make the first 2 end colors 0. So the entire time, like it looks like it's just the boxes and then the background comes in. The background is always showing. It's always being displayed. But it's being displayed with black. And so I also do a thing where I shut down the color ramp if the end color is black. But it ended up being a nice way to sync it because like you show the boxes and those are presented. They're presented twice because I wanted to make it really unexpected when you get the second effect behind it with the background. So it shows it twice as black and then we get these different colors. Another way I ended up saving a couple bytes is this uses 6 and then 4, which is the dark blue and then the purple. And then it uses 6 and 4 again after another color like this. Free McGee, the code's not open source yet. It will be this weekend. And then, and at the end, I also made it black here. And that was actually just to fade out nicer into the layers effect. So that was the other thing. The layers effect sort of scrolls up the color memory the whole time. And so it really it expects all that to be black. And so that was the other reason why it was really important that we use black for all this. But that's basically it for this effect other than the waving character backgrounds. The way I do that is we have that pre-shifted sort of character map where I just take one sort of base set of tiles and I just shift those, similar to what we did with the plasma. So we shift it with X and with Y, and that generates a full character set. And so then what we do is we need to have a way that for every sort of like position on the screen, like select which tile we want to use. And so because I do the X shifts with basically the low bits of, so we have 8 bits for our tile index. And if you treat the low one as the X selector and the high ones as the Y selector, and you pre-shift your data so that that's sort of the case, then you can basically just generate a whole table that does something like that. And I actually want to pull up the prototype of the effect because the code ends up being really simple for this. But it took me a little while to figure out that it was that simple. So we'll run the prototype. And the prototype, of course, looks just like it does in the intro. A little bit different motion because I ended up, for size, I ended up simplifying it even further, just a little bit. So it looks a little bit different. But this also prepares the data. So when I run this, it actually dumps the data. So like if we want to change the glyph, then I have to run this and then it'll generate the new data and then I rebuild the intro, which ends up being pretty convenient. I mean, having this as like a separate tool or a different mode that it goes in to actually generate the data from the make file would be a little bit better, but yeah, who cares? So it ends up doing this. So for every position that there could be a character, we take a constant factor, which is going to be the tile position, where we take the tile y times 8 and the tile x times 8. And then, of course, the tile y is shifted because it's, the high bits. Then we have the constant part and we have a dynamic part. So we get an index into this, which is going to be some static index into this table plus the frame index, which is going to be our motion part. And then we look that up in a table. And so then our character index is this constant part plus this dynamic part. And so all that actually ends up being is this is constant and this is constant. So if we unroll the loop, we actually have this as a constant and this is a constant. And so then all we have to do is offset based on this when we do the lookup and then add these together. In 6502, that ends up being load A with the constant. Then we have the frame index stored in X. So then we can add with carry, which takes care of all of this. And then we can store into the screen, which will actually store the data. And so it's only those 3 instructions. Technically, we should be clearing the carry before we do the add with carry. But as it turns out, it's accurate enough if you don't do that. And it actually makes it fast enough. If we clear the carry, it's not. In fact, I'll even show you what that would look like. For McGee, this is a Commodore 64, and this is a 4 kilobyte intro. It's called Makeshift, if you want to look that up. Makeshift by Logicoma. All of that is expressed mainly in the loop that unrolls it. So it's here. So again, here's the same version of that as sort of how I set it. So we load A with this immediate, which is going to be this. We add it with the dynamic tab plus this thing and then offset by X. So that's how we're able to get the 2 additions. This one's just baked into the address with the add with carry, and then the offset with X is baked into the addressing mode. And then we store it into the screen memory offset plus, static offset. So all of this stuff is static except this X, which makes it really cool. And so we have to loop over tile X and tile Y, and then we output the opcode for load A immediate. So this is literally like outputting bytes, queuing up bytes. That is the speed code for this, the unrolled loop. So we output the opcode for load immediate. Then we calculate the constant part, and we output that here. Then we do the exact same thing for the add with carry, and then finally the store. And then we update a couple pointers. We have to do a lot of self-modifying code in 6502 because you don't have very good addressing modes for doing indirect pointer accesses. So it's really common to just like, in this case, I'm loading a offset here, but I don't think I actually do this for stores in this case. But basically I actually do this for calculating the store address. So it's basically the same thing. But like this initially holds the low byte of the screen address that we're writing to, and this initially has the high byte. And after every character, we're going to increment those as a 16-bit pointer just by modifying the bytes of the opcodes, which is fine because we only ever call this loop once, and it makes it a lot more convenient to write. Otherwise, we'd have to keep our Y register clear, which I actually think is no, because I think this routine clobbers it. But yeah, it just makes it a lot more convenient to just self-modify the code, and that ends up being okay. And then we have to generate the table it uses, which is fine. And that's basically it. So that's that screen. So like I said, this thing is surprisingly technical, and that's kind of what made it really fun. There's that effect. Now there's actually technically 2 more effects, and I'll actually go over the text first because it's a lot simpler. And we'll save the layers effect for last, including I'll show you what it actually looked like before I put it in the intro, and you'll be probably as disappointed as I am that we couldn't put that version in the intro. But I'm actually going to put that in another demo that's coming out in a couple weeks because someone asked me if I had any effects laying around, so that'll be fun. So we'll do the text here. Now this is called FLD text. Whoops. And FLD text, it's called that for a reason. So first of all, it's just displaying text, and it just fades in and fades out, and it displays it on the sinus. Now, earlier, just pause that. Earlier I mentioned we do a lot of things that, like, we can't really move this many pixels. So instead of like drawing the text as pixels, we're going to sort of trick the hardware to move the text around, if that makes sense. So the normal screen is sort of organized as a array of characters. And if we just populate the first row with the text that we want to show, we can trick the hardware into not displaying the screen until a line that's further down by manipulating its scroll counters. And so that's what we do here is we basically just offset where the screen starts. So if I didn't do I also changed the background color and the screen color in order to get this to fade in. And also you'll notice this is using the blackened color memory to display the colors again. So again, more black. So we don't have to change that after the intro. So what it does is it tricks the hardware to a certain point, and then it will change the background colors and then let the screen display for a little while, and then it'll change the background colors again. So we start with black, and then we delay the screen, and then change the colors, let it display, and then change the colors back to black. Vice has some really cool stuff here. If I go into the VIC2 settings, VIC2 is the video chip, and I go into debug borders, then we see this is actually more than any TV would ever display. But it kind of shows us where things happen. So in this case, like the background is black, and at this point in this raster line, I change it to purple, and then I wait a set amount of time, and then I change it back to black. And this shows me exactly where that's happening. And this is about as good as I could do while also delaying the screen display, which is called FLD, which is flexible line distance. That's why this is called FLD text. And you'll see it jitters a bunch. It's not cycle accurate at all because it really doesn't need to be. If we turn the settings onto full borders, this is about as much of the borders you'll ever see on any display. And as you can see, it's well away from there, so we're actually fine. And then the normal borders, what I typically test with. So yeah, a little bit messy, but it totally is within tolerances. So if I go to the FLD text, it's very, very basic. So whenever we have a frame, we're going to copy the text. I actually copy the text there every frame, which is fast enough, and it's just simpler to not have a conditional there. So it always copies the text, and then at the end of every cycle, we just increment the pointer that it copies from, which is actually just modifying this load instruction here. So we always copy the text to the screen, and that's just changing character indices. And then we do this FLD routine. And so all we do is we wait until a certain scan line. This is a really cheap way to do that, just by comparing the raster register. And then once we hit that, then we loop and we start changing the scroll register, which is part of this main settings register. And we just change the scroll register so that the display never thinks it needs to start until eventually we let it go, and then it will display the screen. That's how that actually works. So we wait and do that, and then we delay the display. This is actually kind of both of those steps are baked into this one loop, which is pretty nice. Then I set the background colors, and I do those based on reading from this color ramp as well. So that's how we get it to fade in and out. Then it's going to wait a few lines after that, and then it's going to change the colors back to black. And these are like, this is a little wait loop here. I think there's another one of those here, just to adjust the timing after we've waited till the stuff we needed to wait for. And then it will, change those to black, and then it will go ahead and finish whatever it needed to do per frame, and eventually it will then return from the interrupt, which will return back to the code that's loading the next effect, so it's kind of fun. So there's that, and then of course here's the actual text. A bunch of 40 byte wide strings here, so that we always just load 40 bytes and dump it into the screen. The area between here is basically going to be packed to very small amounts because it's just consecutive hex 20s, which is what space is. And I also changed this text a lot to kind of make it, for example, like I think I did this used to say this is on one line and then another thing here, but it was actually smaller to just do this and then is like this. And I liked it better suspense wise anyway. So I did stuff like that to get the bytes down. Like there were crazy stuff in the end to get everything small enough. Like the last 100 bytes especially were just dumb stuff like that going through. And I'll show you my favorite optimization when we get to the layers effect, which I guess is right now. So the layers effect is, after having done the demo, it's probably my favorite. Let me go ahead and start that up here. Now I actually think because we don't ever reset color, no, actually it'll be all black because of the other stuff. This should work. So this is the layers effect, and it's surprisingly technical. There's basically two layers here. It's kind of meant to look like two layers, and then the front layer is masked by a third layer. But it's only 2 layers. The background layer is always displaying text. So that's made up of 8 sprites, which is how much sprites the hardware actually supports displaying. And as the screen scans, it will actually have to update the sprite pointer so that the sprites will display again, just those same 8 over and over again with updated pointers and updated positions. Additionally, the sprites only have 3 colors in addition to the transparent color that will show whatever, which in this case doesn't really matter because we have nothing behind that. But that's actually a problem because here we have a 5-pixel high font. And so halfway through this, we set up the initial 3 colors, and then while it's displaying this 3rd color, we have to have interrupts there that also reset the colors for the next 2 as well. So it ends up being kind of a mess, but it ends up being pretty nice. It's basically what makes this one particularly difficult to implement is just that there's a lot of scheduling because so the masking layer here is basically just the character layer. And then that's just set so that we have 8 different character sets, I think it was. And then, so it displays all 8 of those and then it will repeat. And those are designed so that the screen will always be scrolling up to 8 pixels upwards. Once it's scrolled 8 pixels, because that's as far as you can scroll on this machine, we have to reset the scroll, and then we have to shift all the actual tile data, all the color data up one row. And so the characters have been designed to sort of be a repeating pattern that's sort of on that 8-frame loop. It's actually 16 frames just because that slows it down, makes it look nicer, but it's only 8 actual animation frames. And so it's really just this simple slash pattern that's sort of designed to first of all counteract that scrolling feel, so it looks like it's a separate layer, and then it also does a little more motion as well, so it kind of looks like it's moving on its own. So that's what you can kind of see here. And all that does is it either displays the color from color memory, because this is a high-res mode, so we either get the color that's in color memory, or we get whatever's behind that, which in this case is the sprites, because they have low priority in this case. So the sprites are doing that thing where they have to have a bunch of interrupts that fire as the screen scans in order for them to display what they need to display. Every 16 frames, we have to shift a bunch of data, and that actually has to be done in a way that's friendly so that those interrupts can still fire while that's happening, so there's a lot of scheduling there. Additionally, to fill in the new sprite data as it's reading the characters, as it's scanning down, it would be really nice to do that. So like the sprites will scroll a certain amount and then they'll shift, and then they'll just do that over and over again. And it'll shift all their pointers when it does that, so we get a sort of a smooth scrolling over time, just like with the color memory. Now, when we do that shift, it would be really nice to just load in the next row of sprite data for the next from the font and everything. But it's not fast enough to do that. We don't have enough raster time to do that. And so instead, that has to be done progressively. And there's a couple other things with the scheduling there that just made it really nasty to write. But it all works. And additionally, we have to like pre-calculate this picture here, and that has to be laid out in a certain place in memory. All that shifting code has to be unrolled, so that has to be in different parts of memory. It became like really complex in those ways. So my prototype is really, really detailed here. The effect itself is just kind of a wall of assembly. Less so now than it was, because I had to cut a lot of stuff for this because of size. So basically, this only shows one masking pattern. So the whole time the screen is masked by this slash pattern. Originally, I wanted to do like the only really dynamic things. Whoops, that's the monitor. The only really dynamic things here are the text itself, and that the text will change color. Nothing else really dynamic here. And then of course the scrolling, but like this is a static picture that it's scrolling through. The text is static that it scrolls through. So it's really just the motion and the fact that sometimes the text will separate. But man, did I have a lot more in my prototype. So let me show you my prototype, and I'll first show it to you as a C64 program because I did get this running. So we'll do this first. So this is the original version of the effect and note that this is running in the emulator, like this works, and I did get it down. This is in the 5K version, this would have been looking like this. First thing you'll notice is, oh, there's no masking, but wait, there totally is. And so it will do the same sort of thing, but it changes patterns. The scrolling here for the colors is a little slower and smoother because it actually blends colors by alternating them per frame. and we get lots of different patterns. And unfortunately, I had to cut like all of that when we actually had to get this down. Hey, John Hunter. I just saw it rep not Ferris built a CPU in. We'll see. My FPGA is behind me, so we'll see. But yeah, and then what you saw there is this is the effect just still running, but then the screen changed color to tell me that it was done. Anyway, so that was the original version of the effect. It's kind of sad that we didn't get to use that one, or that I had to cut out so much of it. Initially, when I cut it down to one pattern, I had that one with the wider slashes there, but then that ended up that needs 16 characters that generates, which means we have to generate 16 different characters per character set, and we have to do the map more expensively. Whereas this one only has one character per character set, so we can put the same value in all the screen memory and everything. A lot of stuff like that. It's just simplified a lot of things. But yeah, so this is the original, and then the prototype. Actually, I probably need to run it out of there, because I think I broke the prototype in the actual demo, in the actual demo folder, when I was changing some of the glyphs, which I'll get to, which is pretty funny. Like as I was changing the parameters to kind of cut it down, I ended up making it so that it doesn't quite run anymore. But yeah, like it'll run for a while and then it'll have a memory access violation or whatever. But it ran enough for me to see that it worked, and so I could put it in the demo. Fun stuff like that. But again, I mean, the effect itself, I don't feel like it's terribly complicated as to what it's doing, but it's how it has to do it that just has a lot of details. So I just made a really detailed prototype. And in fact, my detailed prototype even has, where is it? So yeah, so here's the different scroll text. I played with a lot of different text to have here before I came out with what we do now. And you'll notice something interesting about Wobble's name, which I'll get to in a second. But yeah, this will pack the font and everything, and a bunch of colors and stuff. And somewhere here, I have a VIC bank. Yeah, so here's even the 16K that the video hardware sees is kind of what it's emulating there. And I emulate the like exact memory layout of all this stuff in the prototype. So this is the prototype. Obviously, it looks the same, because it's a good prototype, so it's exactly the same as what we see later. Another thing you'll notice is, in addition to all these other patterns that it has, the scrolling picture here, which is in this case just a plasma, also changes to these slashes, which I also cut from the actual demo due to size. Although that only saved like 10 bytes, but that, I mean, when we ended up 1 byte under the limit, then that 10 bytes was quite significant and a pretty good way to cut costs, actually, because it's not really very important. But yeah, so I emulate like exactly where the video hardware is going to be reading all the data from and exactly what format it needs to be in, just to make that super detailed, because I knew that all of the sort of clerical work that we have to do to move the memory into where it needs to be was going to be the hard part here, and is what sort of makes this complicated. So I spent a lot of time in the prototype just nailing that. And it ends up working out really well, I think. And again, this one also dumps things like the color tables. It looks at the text that we actually use, and it packs out the font. So the font originally is a PNG image. Here, actually, I'll open that up in like something I can zoom in. Actually, where's A-Sprite? Where'd that go? Pull it up in here. So this is the font. This is actually the same font I drew for Demon Blood, which was my Game Boy demo a few years ago. Make sure I'm not covering that up. And it's just a 3 pixels wide by 5 pixels high font. And very, very basic. Although, one of the things I did at the end to save bytes, we were 12 bytes above the limit, and must have been half an hour before the deadline or something. And I wasn't stressed at all, because like I know I can push the deadlines and stuff as long as we have a placeholder in the compo system and stuff. And I wasn't worried, but it was just like I had cut so much stuff, and like we had it so small at that point. It's just like, where do I get the rest of the space? And as I'm watching, I watched the demo a few times, and as I'm watching it, I noticed something interesting. So I had changed the text a lot in order to reduce the amount of characters we use, because every character we use we have to pay for. And as I'm watching this, I notice when I look at Wobble's name, it's W-O, and that's the only W we use. And if I look at Hoffman's name, it's H-O. And the W and H actually kind of look a little bit similar. And so what I ended up doing, this is really cheeky, but it saved like 6 bytes, is I changed the H to be ambiguous. So this was the H, and the W looks like this. And if I put 2 pixels like this, then I get something that could be a W or could be an H. And so then I just changed Wobble's name to Hobble. And nobody will ever know the difference. Actually, this is not the prototype that happens in. Yeah, so now in the real demo, you'll never be able to unsee this, by the way. Then you see here, again, like you don't notice unless you're looking for it, because they look good enough. So this is totally Hobble, it says here, and then Hoffman. So we get HO both places, and then we only store the H glyph, not the W glyph. So that saved 6 bytes, and we had like 6 more left, and I think I got the last ones just by going through by hand. So I had separated the code and the data into different programs, and I could move where those were independently, and I just started packing stuff really tightly by hand and sort of adjusting where those were, and then we got the last bytes and ended up with 1 byte under. So that's what that is. So pretty funny. Now I think that's mostly it for sort of high level overview of how the effects work. Otherwise, I think I need to cut that off, because otherwise I'm going to be sitting here for several days explaining all this and going through this. But again, I'm going to release the code, and you can play with this for yourself. And then I totally found another demo that I can dump some of these effects in, which I'm really happy about. So then they'll actually see the light of day in their full glory rather than in the stripped down versions for this demo. But I'm also happy I stripped them down for this demo and actually got them in there, because I'm really generally fairly proud of this production. So let me undo. Oh, did I close this? Oh, that's fine. I'll just check it out again. So that's it for sort of the effects. The last thing I want to talk about is sort of a bit about how these fit together and a bit about the packing in particular. So by the time I build all this stuff, I end up with something like a 16 kilobyte or so demo. And that has a couple things that are in specific places in memory already. In particular, there's a blank character set that needs to be at a certain place, which is all zeros, but it needs to be at a certain place. And a couple other things. In fact, let me just pull this up for you, and then I'll explain what it is after. We'll do. No, this will be fine. So this is the packing report. And so I made something called Admiral Pack Bar, which is my favorite name for like any tool I've ever made, probably. And it's because it has 4K in it, and it's a packer. So this is the compressor I made for this. And I specifically made a compressor because I wanted to. It actually does about, I think with this data, it's like 100 bytes worse. I'm estimating, because I only tested it when I just had the plasma against like the best compressor for this stuff there is. The C64 scene is really competitive, and that compressor is really good. It's called Exomizer. And at that point, I tested this and Exomizer on that plasma effect. And the Exomizer version didn't run, but it's probably just because I didn't configure it properly. But the Exomizer beat it by like 60 bytes. And if we extrapolate that to that 2.5K to 4K, then the Exomizer version should be about 100 bytes smaller than my version of this, which wouldn't have won us that much, to be honest. I would have ended up just filling that with more precise sync and not cutting down some of the motion on some of the effects a little bit. So it doesn't make up that much of a difference realistically, but it is my packer is a slightly worse than that. But I made it myself, and I totally have room to improve. And the really nice thing is I was able to like completely control what it did in terms of like where it put memory and where it put tables and stuff. And I'm really happy I did this. But yeah, so what this basically shows is this is the sort of unpacked data, starting at where the basic memory starts in the system. So this is, if you just loaded the program as is, then you would get this. But of course, this is, you don't load that. You load the packed one, and then the packed one will unpack itself to this. But yeah, so this is the sort of unpacked intro here, and the colors you see here are basically how well it packed. So or rather, the heat map as it gets hotter is how poorly things packed actually. So this blue stuff is where stuff that packed really well. So here you can see that this was, I probably can't read that on the stream, but this is like 6,100 bytes packed down to 34 bits, which is, I mean, it's all a bunch of zeros, but still awesome. Like it's smaller to just have a big chunk of zeros in the compressed data and have the decompressor just decompress a bunch of crap like this than it is to write the loop that would have set all this to 0. So it's totally worth taking advantage of that. But stuff here, like you can see a bunch of 20s here, which is the space character. So I know that this is the text that's in the beginning of the demo. A bunch of 1s here. So this is a color ramp, a bunch of stuff like that. And the different blocks are usually different effects, although you'll notice the first is pretty tightly packed. And that's how I got the last few bytes, is just packing those by hand. Once basically everything was done. I knew when we had like 6 bytes left that would get us the, like, because you can always tell when you just start moving those things around that there's a little bit of variance. So I figured that would work out. And if it didn't, I could just restart, so it didn't really matter. But yeah, so Admiral Packbar is the packer I made for this. And the depacker is something like 270 bytes, maybe a little more. And then, yeah, packs something from however big this was. In fact, it shows here. It was 14 kilobytes or so down to, 3,800 in this case. Now the packer actually has 2 modes. It has an instant mode and an optimal mode, and usually I run the instant mode for testing, and that is about that fast. If I say packer speed is optimal, then it's going to take a little while longer, and it's going to sit there and basically find better patterns and stuff. In fact, if I show this and refresh it, you'll see it gets a little bit lighter, or actually a little darker rather, a little cooler. And that's because it packed a little bit better, but it took a lot longer. In this case, it took 3.14 seconds. It took pi seconds, kind of fun, versus like basically being instant like it was in the other mode. And the difference in size there, so this packed to 3765, whereas the instant mode packed to 3802. So that's a difference of like 45 bytes or something, which is totally significant enough to wait 4 seconds at the end there. Basically, the packer itself is kind of a bit boring in terms of packing, but it's interesting, of course, in terms of solving the problem with the right method. So it's an LZ-based packer, which has the properties that the unpacker can be fairly small and can also be really, really fast, which is definitely a constraint that we have when our CPU is less than 1 megahertz. So when I run this, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4, about 4 seconds is what it takes from when you run the program to when it's done decompressing. Now, you don't really notice it when you run this. That's kind of the kind of pause you would expect when you run a program on C64. So it's totally fine. I don't even have to do a loading thing for that. But yeah, like that would be significant in some scenarios for this small data, of course, but it's totally fine here. Now, if we're doing this optimally, if we're packing an LZ packer optimally, we have to be pretty clever with the packer, or else things will take quite a while. So like, this is a pretty high-end machine that packed 4 kilobytes worth of data, or about 14 kilobytes uncompressed in about 4 seconds. That kind of sucks, but it's totally good enough for what we did here. And it's not sucky because it's really bad code, because it's not. It's actually pretty good code. I do a lot of searches and stuff to actually find. So with LZ, it's like basically known, given an encoding, how to do an optimal search. The problem is, if you do an optimal search for your LZ packer, you would rather adjust your encoding as well to sort of fit that. And so when your coding and your parsing is dynamic, then you kind of run into problems. What I end up doing is I do an optimal search, which is sort of brute force. Do an optimal search to find a way to parse the data, given a heuristic encoding, and then I find a best encoding that's the best fit for that way of packing the data, and then I do that in a loop. So I take that the new encoding and I try to reparse, and then I take the new parse and I try to find new encoding until it doesn't actually find any more improvements. Now this, I think it has a tendency to get stuck in local maxima, and it ends up being very similar to what Exomizer is doing. Like I tried a lot of stuff here to initially like basically come up with a simpler encoding scheme than what they have in order to make the depacker smaller, but even have slightly worse ratio. But I was hoping it would work out in the end. It just totally doesn't. Exomizer ends up being way better tuned in that case. And then, so this ends up being some sort of middle ground there that still packs a little bit worse. And I would like to spend more time, because like I said, I'll definitely have to do one of these again. I'd like to spend more time on this and try and see if I can beat it, especially now that I have a full intro to test on, which will give me better data. So there may be some interesting stuff there, but yeah. Anyway, that's kind of interesting. Solo Techno, thanks for the follow. But yeah, so I did that packer. That's also going to be part of the open source thing. It's a packer. It's actually one file, which is not the worst thing I've ever done. But it just kind of made sense to work on it that way. I mean, it really doesn't do anything terribly complicated, so just kind of made sense to do that. Actually had a fun time optimizing that, interestingly enough. Thanks, Repnop. I had so much fun. Like this, I worked on this for like my free time in the last 6 weeks or so, and I had so much fun doing all of this. Like, it really wasn't that stressed for time because it's not that big of a project. It was just so much fun. So I kind of actually want to go over how it unpacks. I started actually, like I said earlier, I was making some slides for this. And I want to share this because it has sort of a multi-stage unpacker, which is kind of interesting. So the first stage here, I can actually pull up here's the binary, but it's quite small though. So this is the binary. It's again 4095 bytes. And it's mostly packed data with some unpacker stuff at the beginning here. I don't actually know where exactly it starts and ends. I actually have that information from Kickassembler somewhere if I scroll up here. But it's not that terribly important, to be honest. Basically, the first bytes you have a load address. So on C64, you don't have like ELF or one of the more complicated executable formats. You have the program format, which is just a 2-byte load address, because again, you have 64K of memory, so you only need 2 bytes. So where it starts, and then just the data for however long the file is, and that's enough for the OS loader to actually load the file into where it needs to go. So this is 801 hex, which is where basic memory starts. And then the first bytes here is actually a little basic program, little C64 basic program that is. There's a pointer here that points to the next line of the program, which is a dummy line to end the program. And then right here you have 10, and then the sys command. I think it's these 2 bytes is the line number, which is 10. This is a token for the sys command. These 4 numbers are 2061, which is going to be the actual address that we're going to jump into. So what this says is that we need a line number for it to be in the basic program. And then sys 2061, sys is basically jump to a subroutine in machine code at this address. And where that points to is right here, which is going to be right after that. And then that's our first stage, is so that, I can show you basically why this is. We do that so that when we run this, when we load this, let me actually just pull up let me do it like this. Or actually, I'll do it in the C64 debugger because it'll be easier to see there. And it'll still have the disk loaded. Yeah. So if I do list here in the C64 interpreter, you'll see it has nothing. So list will list sort of the current program. And when I load the 4K, it loads it into this particular address, and it loads it at 801 hex. And 801 hex again is where that basic memory is. And so it's going to load it. And then if I type list again, then we see there's our 10 sys 2061. And the only reason we do that is so that right after you load, you can just type run and it'll go. Otherwise, you have to type the sys with a specific address, which a lot of 4Ks on C64 do, but I just thought that was sloppy. So, yeah, just kind of nice. But yeah, then right after that, is it Control-Shift-R? Yeah, there's my hardware reset. So that's our first stage. The second stage, right after it jumps into this machine code, then we're executing that machine code. The next thing it does is relocate it. So this is like as basic as I could make this look. Let me hide my face here for a second. This is sort of the most simplified visual of the 64K of memory that I could get. We have some system stuff down here. We have the screen memory down here. Or maybe this was the screen. This was all system stuff. I can't remember what I meant for this to represent. Now I do. This was some system stuff and some screen memory. And then here was that basic program that we had. This is not drawn to scale at all. So the basic program jumps into that next piece of code, which starts out here. And this next piece of code, its job is to relocate all of the compressed data up to a different point in memory. And the reason why we do that is, I'm a disembodied consciousness. Explains everything. The reason why we do that is because we actually want to use BASIC to generate a big sign table later. And we don't want to store the basic code to generate the sign table uncompressed. We want that part of our compressed data. So we actually have to decompress over the basic memory again, but that will clobber our compressed data. So instead we're going to relocate the compressed data up here, somewhere in memory, not at the top of memory because there's a bunch of stuff up here that we can't clobber, but up here, actually where the cartridge memory is, interestingly enough. So that's our second stage, is to relocate. Then what we do is, so this is the code that would relocate, and then it jumps straight into this because it relocates the rest of this, which is a little bit more of code, which is the unpacker, and then the rest of that's going to be data. Now, interestingly enough, I actually always, to simplify it, I actually always copy 8 kilobytes from wherever our intro is. Now, because it's a 4K, that will actually copy twice as much as it needs to. But when testing, you vary a lot up, like over and under the limit. So it's very useful to copy more data than you have to, or at least have the ability to be bigger than 4K to some degree. So it actually always copies 8K. So that was the second stage. I don't think okay, here's the third stage, which is actually decompresses. So this is meant to represent the first bit of that relocated part being code and the rest being the compressed data. And then it will just sit there and decompress that. So that's stage 3. And after that, it then jumps, what it actually does is it goes to stage 4. Stage 4 is somewhat interesting. I don't think I have a slide for this. Stage 4, now that we have our basic program and then as well as our machine code and our other data that needs to be here, we want to return to basic. And to do that, we would just basically do a ret instruction. It's RTS in 6502, but it's basically ret if you're familiar with other architectures, to return from a subroutine. And then that would put us back in the basic interpreter, as long as we haven't clobbered anything down here, but we haven't. We've basically extended the basic program. However, there's one thing that we didn't do. So the basic interpreter has a bunch of like tables and stuff that it needs to have in order to store extra data for things like variables that your program uses. And in extending the program here, we actually have left space for those variables, but the Commodore 64, the basic interpreter doesn't know that we just grew the basic program. It could never know that. And so like normally when we load a program, it will figure out where the table of variables is going to need to be because it loaded a file and it just sets the table of variables at the end of that. It's called var tab. So before we return to basic, we actually have to patch that table again. So this will then jump down in here somewhere to a tiny program, and all that program does is sets up the var tab to be somewhere out here and then returns. And when it returns, we're back into basic. So stage 5 is we're back into basic, and then we're going to generate one sign table. In fact, let me look in here to see how I pause, and I can actually show you the stages as they happen. Okay, so it's F10. Good, okay. F11 is unpause. So, oops. No. I actually don't know what's happening here. Did I do caps lock? Screw it. Reset. So we're going to load it, and then I'll walk you through the stages here. A couple of them happen really fast, but this is kind of cool to see. So this is just the system loading the 4K. And when I type run, we're going to hit stage 1. So I didn't have time to stop it, but stage 1 just takes this pack data and just moves it up here. Now moves it here in particular, I think is where that was. Yeah, moved it here. This stuff was other stuff that was already there as far as I know. Let me do that again, actually, because I'm a little unsure. Yeah, so this is other crap that was already there. I can just do this again. Takes a second. I think it's Alt P that does that. No, that was, whoops. Don't mind that. Yeah, so we're going to run. Yeah, I did it again where I kind of skipped it. But then the first thing it does is relocate here, and then it's going to start executing out of here. Now you'll notice that there's a lot of this stuff that's light blue here because that's actually executing the unpacker code, and then you'll see this other part scan here as it writes down here, and that's where it's unpacking this data here. So this is our stage 2. And that happens relatively quickly. And now we're already into stage 3 and 4. So stage 3 then set up the variable table, which ends up being somewhere out here. And then stage 4 is happening now where it's generating the sign table. So it generates this sign table, and the sign table has some interesting properties. The way I do all the sign tables in the intro is they're all basically sign times some power of 2 for the amplitude of the sign. They're all like one phase, and if you need other phases, you can like bake that into how you read it or do some further processing on it. But basically, they're all sine of one phase times a power of 2 plus a bias. That's all it is. So to do that, we generate a base table from basic using just the sign function that the basic interpreter gives us. And we multiply it by 32,767, which is our maximum 16-bit value that we could have in a 16-bit table. So it generates that here. And it's pretty slow. So as it's doing that, we also clear the screen. So you can see it writing here to the table. It writes here, which is where our screen memory is. And it's filling it with this green color, which is this solid character. And then up here, it's changing our color memory to be all black, where normally it's this lighter blue color. Generating that sign table. And then right after that, you'll see some interesting stuff in our next packer stage. I don't remember what the stage number is, but that's just what it's doing. Okay, so right there, you just see it banged all this. So it took that first table and just copied it like 16 times or however many tables I have. And then what it does, so now we have that table with like our maximum values repeated many times in memory. Then it goes through for all those different copies of the table. There's another couple tables. One of them has a shift value. So it goes through all the entries in all those tables and it shifts them right depending on the values while maintaining the sign bit in those 16-bit tables. And so what that does is then, like if we need a table that's going to be -8 to 8, then we shift it right 14 bits or however many it was. 13 bits, I think it is. Anyway, doesn't matter. And we shift all those right, and then we do another pass over those, which is going to bias those. And all that's doing is just adding a 16-bit number to all the entries in the table as well. And that takes care of all of our sign table preparation that the other effects will use, except I think a couple of them will also flip them, and there's a couple other things, but it doesn't really matter. So that's the next stage of our unpacking. And that happens fairly quickly, and now it's already done. I'm going to mute my system audio here because it's gonna get ugly. Hey, Sophia. So then it finished all that, and now what it's doing is it's going to start unpacking the, so now we're basically in the demo. So after it unpacks, in fact, I can show the code here as well. So this is where it did all the biasing for the tables, and then it jumped to initialize the text effect, and then enabled interrupts, and then we're basically moving. And now in the background, while that's running, it's going to initialize the zoom plasma stuff, and it's going to initialize the sine plasma stuff, because the code and the data for both of those effects are laid out so that they don't clobber each other. So we actually just load both while the text effect is running. And so if I just run this, you'll see a lot of this happening. Like this part here, this chunk that looks really repetitive, that's that unrolled piece of code that does the Y selection that I mentioned in the Plasma. The stuff up here, it actually took, so this is the packed character set for the Plasma, the pre-calc stuff, and it unpacked it into the data layout it needs up here into this last bank. It ends up spending a little more time down here writing other more expensive patterns and stuff for the sign boxes. Particularly the code to update the screen there is kind of expensive to generate, so it's generating all that. You can also see it reading stuff up here. That's actually reading the Y table for this, which is kind of fun. Yeah, and then at the end it finished. So now we have the stuff for the sign table, or the stuff for the Plasma effect, and then we have the stuff for the sign boxes here. And then eventually will just kind of finish out its effect, and eventually it'll swap out the interrupt handler with the one for the Plasma, and then we're off. So that's sort of all the unpacking, and now again it's running the Plasma, so you can see it's executing this code here. This stuff, I'm not actually sure what is changing there. It might even be the audio registers, just looking at where that is. I'm not actually sure. It's actually probably the color, the first color of the line, because I think I always write that every frame, because it's easier to just do it every frame than have a conditional. It's slightly smaller. And then up here, these are the character indices. And again, if you look really closely, you can actually see it doing the X sort of zooming and stuff, which is kind of cool. And then there's some 0-page stuff for variables. And yeah, a bunch of random stuff. And then, yeah, you can see the table stuff is going nuts here because we use a lot of tables for this effect, which are basically free because of the way we generate them all. Yeah, it's cool to watch these run through. And then eventually it's going to switch effects here. Now, as soon as it does that, the Plasma's done running, and so we can reuse that memory to do all of the other memory stuff that we need for the layers effect. So as soon as that happens, the first frame that this runs, it dispatches to start loading the layers effect. And so you'll see a lot of this stuff get overwritten as this is going. You can see all this gets overwritten. This right here is actually the character memory to display the wavy characters in the background, which you can't see here. But yeah, they'll come in a second. Excuse me. This whole upper bank here is used for the layers effect for all the data and all the graphics data. So that basically gets cleared and then set to some initial stuff. So it gets all cleared and then generating some, I think this is actually the color picture that scrolls up, the Plasma picture. So it's generating that. And then here it starts generating the character patterns, or maybe it already did that. Now that that's stripped, I think it might have already done that. Yeah, so I think it's actually loaded already. And then, so that's just totally ready to just swap instantly when this is done. And then it goes there, and now we're loading the next stuff. Or displaying the last stuff. And in fact, actually it dispatches as well. The first frame of this, it dispatches to reload the text stuff again as well. So that's all loaded. And so then when this is done, it can just jump back to it can replace its interrupt handler with the one for the moving text like we had in the beginning. And then that'll close it out. And then that's the whole demo. So I really like watching it in this view. I kind of wish I knew about this tool when making this because it would have made a lot of this simpler, and I probably would have spent less time in the prototypes actually, just because a lot of this would have been easier to visualize and easier to kind of figure out, I think. But I don't know, the prototype thing ended up being really, really, really productive as well because it was just like I could kind of relax a bit with all the details and just kind of figure out how things would work on a higher level and then just put them in here, which is really nice. Another thing you'll notice here is you'll see this still reading one of the sign tables while it's doing this. I have like a location in memory that determines whether or not this should move. It actually always does the sign lookup and then sets a variable for what the Y position is, but then it overrides that if it's not supposed to move. So you'll see this. And then at the end there, we actually call the system reset routine. And so what you see here is actually not the demo anymore. It just is whatever the system reset routine does. So that's pretty fun. And then we're back to basic. Now, actually, interestingly enough, it doesn't actually make a completely clean exit, and I don't really know why. I'm not going to look into it because we only had that 1 byte free, so I don't want to repack it and do all that stuff. I've only noticed that when trying to start only certain demos after this one, the disk loading routine from the kernel seems to fail, and I don't really know why. So that's kind of fun. But yeah. Anyway, I wanted to say a little bit more. I think that's basically most of it for like the visuals and kind of how different bits of this fit together. I mean, there's all of this is put together with Makefiles. Like even the packer, the program for the packer doesn't do any of the linking or anything. It just takes in like the big binary that represents the unpack demo and then compresses it and generates the report. But if you look in so I have intro.asm, and this is sort of what that big chunk of data is all put together. So we have, this one has all the stuff for the color tables. It has like linking all the programs for the different parts of the effects. So this is sort of our top level thing here. And again, this is where our little background thread dispatch was. There's the block manipulation stuff, which is like if we need to copy blocks or output to an incrementing pointer. There's some routines to do that because a lot of the effects will do that, especially when they're generating stuff. In fact, I think only when they're like setting themselves up. And then, yeah, all the table biasing and stuff is all here. And also the basic. So I wrote some macros to help me write the actual basic that we use for doing the like the sign table generation. That's what this is. And it's, yeah, pretty basic. I didn't mean to do that. Yeah, and then here's the stuff where it resets the var tab and then returns the basic. Interestingly enough, when it's using basic to generate the tables, it's like I played a lot with what the best way to do that was pretty early on. And the best way I found to do it was have basic generate, like do a loop of 256 values and have it store the results in a variable that's suffixed with this percentage sign. And what that means is that the variable is going to be an integer variable. And the integer variables in this basic interpreter are going to be 16-bit signed, which is exactly the kind of values that we want to put in our tables. So every iteration, it generates the sign, puts it in that variable, and then actually jumps into a subroutine in machine code that goes and grabs the actual data from that variable, the 2 bytes, and puts them in our table and then increments its own addresses and then returns to basic. So it goes back and forth, but it ends up being very small that way. So that's kind of cool. Kind of cool how that works. And so that's what's actually doing it pulls the data out of the variable and puts it in the tables, and then it waits for scanline 0, and then it changes like the background color and updates the screen data, and so that's how we get sort of the smooth stuff that happens there. So I think that's pretty fun. And then, yeah, so that's pretty basic. And then, so like the top level packing stuff, we take that intro, we get intro.bin, which is just this big hunk of binary. And in fact, our report that I showed you earlier, wherever I put that window, I don't know where I put that. Anyway, actually, I'll pull it up again. This report. So this report here, the data you see here is exactly the same data that's here. Exactly the same data. Sorry, Sophia, I don't think I want to jump back and explain that again, but you can watch the VOD when that's up. So that becomes like that one blob, and then that's packed by the compressor. And then in makeshift.asm here, this is where I put like the auto start and actually sort of link everything. Cause like normally when you get a packer program, like an executable compressor, it's going to do the like slicing up the data and relinking it and linking in the decompressor and all that stuff. And when I was making this, I was like, well, if I just kind of make it for this one intro, which I'm going to do anyway, why don't I just use the assembler, which already knows how to do all that, and then I'll just make the program that just does the actual compression. So that's what this is. So this file, makeshift.asm, is actually has the auto start, which is our original basic program that jumps into the decompressor. And then this stub in particular, this is where the relocation happens. And then this is our decompressor, which is supposed to be relocated at this address and all that stuff. So we kind of rely on the sort of compressor or the assembler to do all that linking stuff. And I even, because this is a macro assembler, it has a lot of things like conditionals, and you can print out errors and all this stuff. And so this will even like I can calculate the total size of the output and just say like, here's your total size And if it's greater than the max size, which is 8K, then we can't actually compress this because it won't decompress. And then if it's greater than 4096 bytes, which is the target size, then it'll print a warning and say how far above that size we are. So this was just, useful output that a packer would do, and I could just kind of do it in the assembler. So I was actually pretty happy with that solution because I think I saved a lot of time by doing that. So that's more or less how everything fits together. The last thing I want to talk about a bit is the music. Now, Hoffman would be better at talking about this, but this is 1K play. This is formats driver. As you can see, I put a thing where I slightly modified it because I just did some kick assembler compatible stuff. And then Hoffman, of course, replaced the music. And this, I didn't really dig much into this code myself. I kind of treated it like a black box. But it's kind of funny because Hoffman literally had to code the music. So this is the data. And he literally wrote this by hand. I mean, he had an example song, but yeah, sitting here doing all this stuff, pretty crazy. I don't really know how any of this works, to be honest, but I think it's really, really cool, and I wanted to show it. So when we say this demo was made in 100% assembler, like we mean it. I mean, other than the tools and some of the data processing stuff, but yeah, all the code and the content here is assembler, so that's pretty fun. But yeah, thanks to Format, by the way, for letting us use that. It was super helpful. I think it's public anyway, but still super nice that he pointed it out and that we were able to use this. Just like I had to cut down a lot of the effects, we also had to cut down a lot of the song. So it actually had, right now the song sort of has one sort of emotional curve where it sort of builds up and then breaks down. And then the original version of the tune, of course, actually had two sort of humps like that. And we kind of squashed them together once we realized I only had enough content to fill sort of one. And I think I at least have that version on an old branch. Let me actually pull that up because it'd be kind of cool to play. So I need to go back in time a bit here. Yeah, there's the 12-inch mix thing, but I don't want to rebuild it. It would have been nice to just see which commit that was from. Oh, unless you actually have PRGs in there, then I actually have it already. I'll just look for that. Yeah, actually, okay. Oh no, it's just the file here, but I can actually do that. So this part's kind of annoying because in order to pack this, we have to do some cheeky stuff. So what I'm going to do is I have this also checked out another branch. I'm going to just make a mess here. I'm just going to delete this, rename this to music. And then when I build this, it'll give us that. So we have to, oops. So it's on a different branch, so I have a separate checkout for this. So I do make test SC, which is going to test it in the emulator. And then we're going to have the song. And then what I need to do, this is where it gets cheeky. So I have to, let me pull this up. I have this here as well, and I go into the new music.asm, and I need to copy out all this stuff here. Because I changed a bunch of like the alignment stuff in the beginning, so I have to just copy the data. I can't just replace the file. So we're going to copy the data from here into here. This is why I didn't want to swap out the music anymore at the end of the intro, by the way, Hoffman. And then what I have to do is the preview thing here actually pre-calculates some table stuff. So we have to actually go look in the memory and grab those. Not the greatest workflow, but not the worst either, to be honest, because we weren't doing this that often. Mostly Hoffman was able to work in isolation, and we would just kind of update when needed to. So I need 1E and 4E. Oh, we're not even at the best part where I probably have to relocate a bunch of stuff. Yeah, I'm actually not going to do this to put back in the demo because I could just run the preview one here. We'll just do that because I just realized I have to relocate a bunch of data and stuff to actually make that work. But I can just play this. So set this up here. Here. So the beginning is basically like the same. Sidechain by hand. I don't think this is correct, actually. Because that is supposed to go into a different part with a lead in it. That's cool. Technical difficulties. That should have been the one. Unless it didn't rebuild or something. Here it is. Oh shoot, hold on. I'll play it again so you can actually hear it. I can hold space for... That's funny. This sounds like death, by the way, when we do the fast forward thing. And this part's roughly the same. and then it actually loops again. But yeah, that was extra 100 bytes or so. I think it was a little more than that actually, and then which was very much appreciated at that point. So yeah, and it says not only did it reduce space in just making the music smaller, but of course it also reduced the amount of time we had to fill with visuals, which then of course in turn also makes that smaller. 109 says you should have just made an 8K. I don't think so, because like we basically would have had to double the amount of effects that we would have had and everything into an 8K. Like I thought about getting a pixel artist or someone to do like a logo and stuff, and it just didn't feel right. I like 4K. By the way, I was reading a bit of the chat up there. I should actually explain that. Why I did basic in macros. The reason is actually because the basic that's in the byte representation of basic isn't one-to-one with the text representation. And so I did a lot of these macros in order to like sort of abstract the encoding details, but allow me to change this easily and do things like refer to other line numbers semantically rather than like having to sort of type those in. So I ended up making this a lot nicer. Although you'll notice here I'm using, for the line numbers, I'm just using the same one over and over again. It turns out the basic interpreter will interpret this just fine. However, if you list this, it'll just sit there in a loop, replaying the first line over and over again, which doesn't matter because this is the basic program that we overwrite when we decompress. We overwrite the stuff with this. So a user never has an opportunity to actually type list by the time that actually runs. So it's, fun stuff. And it's slightly smaller because it compresses better. So fun stuff there. This is actually just full of like tiny tricks in order to like get stuff smaller. Like the way that sync is done is really, really tiny. Just overall, I'm just like really proud of this thing technically, to be honest. So yeah, I definitely hope to do another one of these. This is pretty fun. Call copy protection. Sure. If anyone tries to list our basic, it's going to repeat forever. Yeah, copy this. But I think that's basically everything I have to go over this. I can take a few questions, and then I'm going to head out, I think. But yeah, thanks guys for hanging out, by the way. This is really fun for me to share, and I hope you guys gleaned enough from this. It's a bit hard to explain some of these techniques without assuming a lot of knowledge about the C64. So if I skim stuff like too high level, hopefully the code helps. But I can, BZ2 compressor, no. If there was a hardware divide and more memory, actually, if there was a hardware divide, then I could have gotten away with at least a little bit of arithmetic coding. Because we actually have enough memory to store enough context for that, but not many. But yeah, the speed is another problem, of course. LZ is a really good fit for this, and then it's just like the magic is in the encoding details of how we encode the lengths and distances of our references into the previous data. The demo is called Makeshift. I can post the Poet link. There you go. There's Makeshift. Also, some of these comments make me laugh. There's a couple that just say, "Oh, this is good for a 4K," and my response is like, "Isn't that just good then? Because it's a 4K." Yeah, whatever. Rip Knob, not really demo stuff, but I saw a thread on RASM, and apparently storing stuff on the stack and immediately reloading it happens a lot on programs compiled with 0. Oh, I'm not that surprised. Not that surprised at all. Like you'll see in when I'm doing the emulator stuff, you see tons of that in that code as well. Yeah. Just because a stupid compiler is a lot easier to write that does that. That kind of stuff. that's a bit funny. But yeah, I think this is super fun. So this Sunday, I'll be back on streaming demo stuff on Sundays again. And then next Thursday, we'll be back on the emulator stuff. This was just a lot easier because I'm giving a little presentation about this at work tomorrow, and it's all fresh in my head. So it's easier to just do this today, and then I'll have my head clear for this weekend. But my Amiga has arrived. However, I don't have a way to get stuff onto disks for it because it's different formatted than MS-DOS. So I've ordered a disk drive replacement for that'll allow me to use USB. And my MSX has arrived, although it's at Tomco. I don't think I'm avoiding the bug at this point. I've done 10 consecutive streams about that bug. So I'm not accepting that, even joking. I am not avoiding that bug. My MSX has arrived, but it's at the post office, so I got to pick that up on Saturday. So this weekend I'll probably do some more old school stuff, either on the Amiga or on the MSX, just popping up an assembler and setting all that up and just seeing what I could do, in a short amount of time, because I think that'll be fun. So yeah, that'll be Sunday. But yeah, Fuse is pretty rad. But yeah, so thanks guys for watching. I'm going to go and leave, and I will see you next time.